At the same time, you do have a softer material, so if you were to have a brittle mode, you may not pick it up in your testing, but it will happen in the actual service because you're correcting okay for the flow of the material, but you're not capturing the effect of the hydrostatic pressure in terms of forming voids because you're just really reducing the load on your system. So if you play fair square and say I know I don't have any brittleness issue, you can use these accelerated method in playing with the temperature, but you're very, very tied to making sure that all you care about is the flow of the material, that there's no issues in terms of forming voids, in terms of environmental degradation. So this is by how much some of the materials would look like. This may be PVC or polyethylene. I don't remember. But if you're looking and doing a test, what they call the creep modulus is essentially the load, the stress you applied, and the total deformation you get after 100 hours. So if you measure that after 100 hours or after 50 years, you get a factor of at least 2 of difference. So it's very significant how much you're going to continue to elongate your material if you keep it under load. And it's part of what people are willing to deal with. You will change that number if you change the molecular weight, because that is it's the molecular weight is really what takes you from taking all of that strain, that viscous flow inside the material. So effective molecular weight. This is so. I need to say this. If instead of applying the load just one time, I decide to fluctuate it, I essentially accelerate the creep behavior. So with polymers, in terms of studying cracking, it's common to do fatigue loading, so applying a cyclic load as opposed to just a constant load, because you can run your experiment in a couple of weeks as opposed to having to wait 4 to 6 months. It's not perfect, but if you can show, looking after the fact that how the material fractured, that it's fracturing in a very similar way, you have a good justification for it, because you're looking at the same mechanism of separating the crack. And we'll talk about a little bit more about how separating the crack in the next lecture. This is something that happened a number of times. Yes? Anytime that you weld, you end up with a fusion line. So if I have one material here, and it's got all the microstructure, and I come with the other, it's got all the microstructure. The time that you have for mixing the two is very important in terms of when you're hot at high temperature and being able to take that long end of a macromolecule and getting into the other guy, because that's what's going to give you long-term strength. If you don't get that, you have a big problem. So one way to make joints out of plastic that is common with these type of pipe for sprinkler lines is to use a solvent cement. So you come into that interface and you put acetone and other solvents that will essentially locally reduce your melting point and make things move around over a period of time that's sufficient to move everything. So a lot of time you want to apply heat and protect the area to be able, or add that solvent to be able to intermix. If you're trying to do it very quickly, I think you have your answer. It's not going to be all that great. So that's why I'm trying to give you some of the concepts, so you eventually you get to answer your own questions. Any other related questions to that? Because we're really in the core here on how this works. Yes?
I just had a question on this. Maybe we're going to get to a molecular weight. But you said, so the last time you said it makes it harder to basically slip the chains.
Yes. Yeah.
If I'm trying to Or do I look at one of these charts and kind of
So if you want to play with the tensile test type of behavior here, if you want to play with the tensile test type behavior, you're looking at the side of your side groups in terms of how much mobility you're going to have. You're never going to be able with polystyrene to get the stuff you get with polyethylene. So there's a certain ratio on how much you can actually stretch it. Most of that stretch doesn't involve the movement over a long distance that I talked about. So I could make that joint quickly and have it look good during a tensile test in terms of the load it takes to break it, if it's all smooth and everything. If I put a notch through it and I need a crazing behavior at the tip of it, that's where the molecular weight comes in. So there's much less effect of molecular weight in a tensile test where I reach 300–400% strain than when I'm trying to really separate the two components. So that's what happened in crazing in notches. So the impact energy for polymer will depend on molecular weight a lot. The downside is molecular weight is hard to measure. So a lot of times the STM standards will give you a viscosity, a melt viscosity index that just kind of tell you a little bit how long the chains are, but they won't give you a number most of the time. So you almost have to test the properties, the creep properties, to know that you got exactly what you were looking for. Yes?
And then when you want those chains to interpenetrate, when you're doing the
Yes.
It's you want the relaxation time of the rotation tube, not the polymer inside the tube, right?
Yeah, so that's right. You need a large distant movement, so it's a viscous flow, and that's why you need heat to make it happen. Very good. You can still add, so on a solvent cement, there's still some molecules that typically in the goop that you put on. These are a little shorter, so they're going to be not exactly as good, but they'll be able to move a little bit better also. So adding some filler can help you make that bridge, because the longer ones, they're harder to bring together. And typically you make the joints so there's not as much load on them. It's a socket type connection, so it doesn't have to be as good as the pipe itself. All right, well, we made it. Let's go through some of the examples before we summarize. So I brought this. I broke it a few years ago. It's from the 1990s. They made fun of me when I showed up to the repair shop with it. So the cap went off here, and it failed on the side of the housing here. And it's not that I was using it more. It's because this material had a time limit in terms of the inhibitors and the oxidation, the antioxidant package that comes with it. And when you exhaust it, now it becomes very, very brittle. It doesn't have anything to do anymore with how good the molecular weight is. You can start breaking chains because you have oxidation reactions going on. So the oxidation is one way to break chains. The sun, the UV light, is also a way to break chains. You need something like that to break the molecules inside the material. Solvent, even oil, is a way to break chains. So I'm showing here a cross section. These are high pressure. These will be used at 180 psi pressure, so 2 or 3 times what's used in regular water for sprinkler systems. And this side is a cut. This side is a slow fracture, and you can see that there was a residue inside the pipe that we associated with some form of oil introduction from fittings. So if you have a plumbing system, you'll have parts that are threaded, and you have other parts that will be plastic. And if you get the oil moving from one to the other, it doesn't necessarily work well. So it will essentially allow, well, oil is a great lubricant, right? So a simple way to think of this is at the tip of our crack, and that's where we're going tomorrow, talking about a little bit more about cracking. At the tip of the crack, I want to take the molecule and say, you're going this way, you're going this way. If I put a lubricant there, yeah, it will go more easily. So that's just the basic idea behind saying, well, be careful with respect to what you're going to put your polymer in. And we'll talk about